Topological physics is probably one of the most interesting things about condensed matter physics in general. It occupies a lot of the research space, and it's interesting for various reasons. Today, I'd like to discuss a one-dimensional topological model called the SSH chain and its time-dependent variation, the Rice-Mele model, and show how we can start to understand this using some simple numerics, even though you can attack this problem analytically. So for the rest of the video, I want to introduce the model, the SSH model, and its time-dependent partner, the Rice-Mele model. Then I want to go into kind of what the physics that we're looking for, or expecting, or trying to extract, really. And then we're going to code the rest in Aleph, and we're going to see these, hopefully, some topological physics at play. So first and foremost, the SSH model is a 1D model of non-interacting fermions. So we could just think of a single electron hopping through a 1D chain with two fermionic modes or sublattices per each lattice site. So we can see here in the expression that we have two kinds of terms, really. We have two kinds of hopping. So we either hop within one site in the same unit cell, but between the two different modes, here labeled A and B, with some amplitude V. And we call this the intracell hopping. And then we can also have cell hopping. We can have hopping between the two cells, but they're not going to hop directly to the same mode. They're going to hop to a different mode. So in the second term here, the intercell hopping couples mode A to mode B with, and in this case, we're taking the modes to hop left and right equally. You could think of like the two crazy cases where you have either strong hopping between the two modes on the site that dominates, or you could think of the other limit where the hopping between the sites, and the coupling different modes dominates. So we call this the dimerized limit for this case here, where V is much greater than U. And this corresponds to a dimers because basically the electron just wants to stay on the site and everything is kind of disconnected. Whereas in the larger U case, we actually see that hopping is more favored in general, and so we can move around. In between these, there's a so-called fun topological phase. And so what we're going to do is, one thing you can notice is that because there's two modes on every site and then there's open boundary conditions, you can think about pairing kind of sites together. And if the couplings are just right, then the modes at the end will actually be left alone, and they become kind of localized just to the edges, and we call those edge modes. Now this turns out to be topologically protected. I won't go into detail about all the topological physics at play here. There's a couple ways to see this by establishing a winding number or calculating some Berry phase. But what we're going to look for is we're going to look to use the fact that these edge modes are there in the 1D SSH model, and then we're going to look at the time-dependent version that I'm just about to introduce. So if we now make the couplings time-dependent and also add a staggered on-site potential, we get the following Hamiltonian below. So we're going to make V of t, W of t, and U of t. Now I should preface and apologize. The V here will be the same, but the U here will be different. So the U will actually become the on-site potential, and W will be our intercell hopping. So we kind of have this time-dependent Hamiltonian now that we're going to look at, and we're going to choose a very, very specific choice of time dependence for our parameters. So here we're going to have the intracell hopping be 1 plus cosine of omega t, where omega is some frequency. We're going to leave the intercell hopping to be 1. We can always choose 1 to be fixed in this setting. We're just going to pick it for it to be W. And then we're going to make the on-site potential that's staggered between the two to actually vary with time as well. Now, the goal here is that we're going to be able to actually take these edge modes if we're in the correct phase, and we're going to pump them from one side to another. So this is an adiabatic charge pump. This full version is just called the Rice-Mele model in the literature, whereas this specific choice is derived from a very particular control freak scheme for charge pumping. This is just a smooth continuous one that we care about. Now, what's cool is that this system, this 1D system, is actually a insulator. So there's always a gap, except at which, when in the first model up here, when V equals U, at which case the gap closes. But on either side of this, there's a gap. So what's kind of cool is that with this protocol, we're going to look at the instantaneous eigenstates, and we're going to see that we're actually going to find a way to close the gap. So we're not going to make bands in the translationally invariant sense, but we're going to have some bands in real, like some the spectrum of the Hamiltonian. We're going to look at it at every point t, and we're going to see how it flows. Now, what should happen the physics says that while we pump these charges, because of the physics of the SSH chain, we're going to take one edge mode on one side and we're going to bring it to the other, and the other one vice versa. And by doing this, we're actually going from a low energy mode to a high energy mode and vice versa. And so what we should see is we should have like a bands, and we should have some kind of connection between the two of flowing the edge mode. Now you can also look at the states, and you can make this a little bit more practical and hands-on, but for this video, we're just going to focus on looking at the spectrum. Now, what we're going to do, so now I can put this way, we're going to get some code. So first what we're going to do is we're going to build the Hamiltonian at each time t. We're then going to diagonalize it. We're going to get the spectrum for some parameters, for some given t, and then we're going to go throughout the whole cycle, and hopefully we're going to see these edge modes appear. So first what we're going to do is we're going to just make a helper function that will take in the number of sites at a time t and a frequency f, and we will make an operator sum. Then we will make our couplings at that given time, and then we're just going to build the operator sum like you would do any other operator sum in Aleph. So what we're going to do, here I'm making, because we have 2 degrees of freedom per site, 2 orbitals, we're just going to have to double the number of fermions we have. So here we're making, so they're all fermions equally, we're going to take all the even sites to be sublattice A and all the odd sites to be sublattice B. So in total, we're going to have 2 times the number of sites that we put in here as the number of fermionic sites that we have. But in terms of unit cells, we have just this number of sites. Then we're just going to strictly add in a hopping between the intra-cell hopping, which is coupled by V of t. So we're just going to add this with the hopping operator, which does it's the Hermitian conjugate of, so it's the full hopping, the hopping left and hopping right of equal amplitude. Then in the case where I, which is the index for the unit cell index, if this is not at the maximal value, then we're going to add the nearest neighbor hopping. This is just a little trick to avoid having to add in the last term, because this depends on n-1 sites, because we're going between unit cells. So here B will be sublattice B, but B plus 1 will be mode A on the following unit cell. And then lastly, we're going to add the on-site potential. So this will make all the difference for us in our physics. And so we're going to go ahead here. So this is just the number operator, and we're going to return the operator sum. Now, that's basically all we had to do. Next, we're going to set up the driver code. So really, what we need is the number of sites and the number of total modes, which will just be 2 times the number of sites we put in. The frequency we're going to leave as just 1 for now. You could play around with this, but it's sufficient to just have it to be 1. We're going to choose a number of, let's start with 20 time steps. So we're going to break out our whole periodic. So here in this case, the pumping scheme that we've picked, or the time dependence of the parameters, is periodic. So we're gonna leave it as is for the moment, and you're gonna see it's gonna look very pretty. And as such, we're gonna go from 0 to time 2 pi. So we do 1 full period, and you can play around with this. This is all fun. But for the plotting, I'm just going to normalize it to a factor of from 0 to 1, just so it's a little bit cleaner. Okay, so this will be for plotting. Then for data collection, we're just going to make a matrix, and we're just going to store every row or column how we kind of care about. So here what I'm doing is I'm saying I want a number of t-step rows, and then I'm going to set rows with n columns. So I'm going to put the energies into every row effectively. And this is going to be useful because since we're plotting as a function of t, I get the spectrum, and it's going to give me all these values. Now, if I want to see the spectral flow, or I want to see actually how the spectrum is changing, I want to kind of line up the values so that, like, actually the next one, how they would shift, rather than, and kind of look at bands almost. These are strictly not speaking bands, but how they form kind of energy bands. This is what we're trying to aim for. So by putting in a matrix, it's just easier to index and pick at which time we want to do this. Next, we're going to time evolve and get the spectrum. It's fairly simple. So we're for looping over the total number of time steps. And at each time step, we're just going to set that our time step is equal to our increment times the step number. Then we call our function. We say make sum. We have to feed in t. Here again for omega, I just put it to 1. You don't have to modify this. Now here comes the kind of the crucial step, which is really what we're doing is we're going to cast our operator sum into a matrix, because we want to get our Hamiltonian out of this. But in Aleph, because we're quantum many-body first, we assume, if you don't specify, that the Hilbert space dimension is 2 to the n. Now here, our Hilbert space is not this size. Free fermionic systems are linear in system size, so much more efficient to tackle. So what you just need to do is you can still use the matrix function, so it'll make a matrix out of O. You just need to give it the option and tell it that we want to cast this as a fermionic single particle Hamiltonian. This is the goal. And all you need to do is use the bar. The bar here says and. It's like an and operator. Okay, hard part done. Then we pass our matrix to our eigensolver. And we're just going to specify the option here that it is Hermitian, just to give it a little speed up. It'll make it a little bit faster to get. So this is a full dense eigensolver. This will just give you all of the eigenvalues. Then we're going to take the result object, and it stores the eigenvectors and the eigenvalues. So here we're going to ask for the eigenvalues, and we're going to just take the real part to make sure everything's okay. And what we're going to do is we're going to set the row of the ET matrix as the eigenvalues we just got. Here I'm just doing the transpose because in general it returns a column. I could have done this the other way. You can pick a preference. So I did it. And we're going to make sure that we set the stepth row of this matrix to be the eigenvalues. Okay, now that's the calculation done. So now to handle the output, what we want to do is we want to store. So in my plotting video, what I did is I used the kind of the method way where I would take figure, and then I would do like a line or x-axis, and I would chain them this way. That's not the only way to do it. Here, I'm just storing the figure into a variable, and then I'm going to modify the figure by calling the methods this way. So I'm going to take, basically, I call these bands, again, they're strictly not speaking bands, but I'm going to take all the different flows or the bands of energies, and I'm going to plot all of them one at a time, line by line. So as we're flowing, we'll see the spectrum form stacks of lines that we care about. And one thing to be careful here is that you can convert between matrices, arrays, and lists. This is fine. You just need to be careful about the little details. So here so T of S, this is a real, this is a real matrix type. Because it's a real matrix type, you need to convert it to a list. When you do so, it takes all of the contents of the list and it puts it into another one. So all of the array of the matrix, sorry, and puts it into a list. So you need to unindex the first one. So it takes all the contents. So you just need to add this little zero call here. So it doesn't put all the contents into just one, into a single list. It's a list of lists. And same thing again for the column now that I'm extracting, which is the band. So it's one time evolution here. We're going to give it a title by just saying the Rice-Mele model spectrum. Pick it how you'd like. And then for the x and y axis, we're going to give it names. We're going to say this is the time step t. This is the energy en for the y axis. We're going to make the name location occur in the middle. And then here are the axis labels. These are what in matplotlib you'd say the ticks. We're going to show the ticks here. So we're just going to make sure that we have a sub-option map that just does show true to make sure that we see it. And then we're going to save the file. So here I have a folder called Topological Physics, and I'm just going to path it directly, and I want to call the figure RM spectrum for Rice-Mele spectrum. So okay, so let me just open up my console here. So right now I'm going to launch on the interactive agent that we have. So I'm just going to press play. It's going to upload, perfect. I give you some metrics. This is very, very fast, of course. I'm going to go to my file. So in my folder, I have Topological Physics. I have a markdown file that I was showing you guys earlier. And now I can just select open my figure, and we get a nice little animation here. So what do we see? So x-axis is time, and here are the bands, the so-called bands. This is the instantaneous spectrum as a function of time. And so as we move along with t, we see that the lower, like the closest bands to the gap, there's actually a crossing of the modes. Now here the colors are actually a bit deceptive. So here, this is purple and purple again, even though what's really happening is that this mode is being tracked and it's actually going into the lower band. And now because it's periodic, this is going to flip. So actually, let me do something real quick. Let me do the following. Let me make the frequency twice so the cycle happens twice so we can see this a bit better. Again, life is good. Beautiful animations. So you can see here, so as the cycle begins, so here I've just doubled it, so we're seeing the pumping scheme occur twice. So this would undo this would make sure that we actually get back to the original state. So this bottom band is actually going down, it goes into the lower band, and then because the pumping scheme keeps pumping them circularly, or across each other because they're in 1D, this would actually go to the other side here. And that's really cool, but the resolution doesn't look too great. That's a fair criticism to have. So what we're going to do is we're gonna up this to a bit. So let's do 40 sites, so a total of 80 modes. Then what we're going to do is we're going to turn this to 40 steps, and it should still be fast, barely changed. And if we look at this, it updates. There we go. So now we see the spectrum is much denser in the bands up here, and we really see this nice kind of flatness occurring. Now, one thing, if you don't believe me, you can absolutely take the same code and you can look at the instantaneous eigenstate at the bottom of the band here. So you need a criteria to do this. So you can't just if you pick out an eigenstate, you want to make sure that it's truly an edge state. You need some kind of spatial criteria to determine if it's at the edges. That's one way. But if you were to track the correct eigenstate, you would see that this mode is actually going from left to the right, or right to the left, vice versa, depending on which phase the model is in. And so you could determine it that way, or you could look at the Chern number and you could know if there's a crossing from an up or down, or down up band in this case. Okay, so that's a good next step to do. And you can definitely extend this into 2D as well, and you can keep track of all the terms that way. If there's some interest in more topological things, I would be glad to keep going and actually promote this to a 2D system as well. And let me know in the comments if you'd be interested in that. So thank you very much for your time.